The sudden detonation of a German torpedo instantly severed the structural spine of the British steam tanker SS Coimbra. In a fraction of a second, the routine rhythm of coastal navigation gave way to the brutal physics of tearing steel and shockwaves. Sealed within the heavy steel bulkheads of the vessel was a massive payload, approximately 2,700,000 gallons of lubricating oil, with other petroleum products carried in the ship's fuel and bunker systems. This immense cargo was suddenly exposed to the raw kinetic force of a submarine attack. Fire broke across the stricken tanker as the unescorted SS Coimbra became a burning beacon off the coast of New York. The loss occurred in the bitter winter of 1942. During this early phase of the war, German submarine commanders exploited a dangerous weakness along the eastern seaboard of the United States. Merchant traffic often moved without escort, and shore lighting made the coast a lethal hunting ground. The submarine U-123 did not need to solve an elaborate geometric puzzle. It only needed a target. While proceeding eastbound along the southern shore of Long Island, the U-boat spotted the dim navigation lights of the SS Coimbra and closed on the unescorted tanker. Slow, vulnerable, and alone, the vessel presented the kind of target profile German commanders had come to expect in the opening phase of Operation Drumbeat. The first torpedo struck the starboard side of the hull just aft of the main superstructure. The resulting explosion ripped through the outer plating and ignited the flammable material near the impact zone. Fire rapidly consumed the midship section, yet the vessel initially remained afloat. The engineering crew faced an uncontrollable blaze, while the structural integrity of the hull was severely compromised. A massive thermal gradient formed across the deck plating, warping the steel before the ocean could quench it. Minutes later, the submarine commander fired a second torpedo as a final coup de grace. This weapon slammed into the starboard side beneath the funnel in the area of the engine room and after cargo tanks. The dual trauma was too much for the steel framing to withstand. The vessel burned, flooded, and settled rapidly by the stern. Within minutes, the SS Coimbra was gone from the surface, and the broken tanker came to rest on the seabed in 3 major sections. The exact sequence of tearing, falling, and impact can only be reconstructed in broad strokes. What remained was a violently deformed wreck field, bow, midsection, and stern separated by the force of the attack, the sinking, and decades of movement on the ocean floor. The surface fires were swallowed by the cold water, leaving oil, smoke, and scattered debris above the place where the tanker had disappeared. The immediate chaos of combat ended, replaced by the silent, static environment of the seafloor. The rapid descent was driven by flooding, fire damage, and the sudden loss of buoyancy after 2 torpedo strikes. When the fractured pieces of the SS Coimbra struck the ocean floor, the kinetic energy of the impact caused further deformation of the steel plates. Bulkheads buckled and heavy engine components were torn from their original alignments. Yet, despite the catastrophic trauma of the attack and the violent collision with the seabed, some internal tanks remained capable of holding petroleum product. The inverted and damaged geometry of the wreck trapped oil beneath sections of plating, while cold seabed temperatures made the remaining cargo thick and sluggish. The pressure of the depths enveloped the wreck, leaving the surviving oil pockets sealed inside a cold and dark environment. The unescorted vessel had entirely vanished from the surface world. The survivors were left to face the freezing conditions of the winter ocean. For decades, the exact condition of the shattered hull remained a mystery. The SS Coimbra became a forgotten casualty of a global conflict, obscured by deep water and shifting ocean currents. The danger was no longer the original cargo figure, it was the fraction still held inside degrading steel tanks. Hundreds of thousands of gallons remained large enough to matter, turning the wreck from a war grave into a silent environmental threat off New York. The ocean had hidden the wreckage, but it had not erased the risk. For years, faint rainbow slicks appeared and reappeared on the surface of the Atlantic. These intermittent sheens were not the result of a recent maritime accident. Divers and fishermen had reported signs of oil from the wreck for decades, and by 2015, satellite-linked pollution reports were repeatedly pointing responders back to the Coimbra site. They were a distress signal from a dormant wreck that had retained oil beneath surviving steel for decades. That containment was fragile, not permanent. For over 7 decades, this hydrostatic equilibrium held firm. The heavy cargo rested quietly in the dark, entirely isolated from the coastal environment above. After 77 years of electrochemical exposure to cold salt water, that balance began to fail as the outer steel envelope degraded. The original 1937-era steel was never engineered to survive underwater indefinitely. The chemical reaction between the seawater and the iron steadily ate away at the structural framing. The ocean slowly dissolved the sacrificial metal. Rivets rusted and lost their mechanical grip on the heavy plating. Microscopic fractures in the hull gradually expanded under the constant, sweeping stress of the bottom currents. As the steel thinned, the hydrostatic balance began to shift. The external water pressure could no longer perfectly seal the tiny gaps forming in the aging hull. Small quantities of the oil slowly began to slip through the newly compromised seams. Those surface marks turned the hidden leak into traceable evidence. The recurring anomaly pointed directly back to the resting place of the sunken vessel. Each visible slick narrowed the problem from suspicion to a mapped failure point. Every rivet that failed and every steel plate that deteriorated brought the submerged wreckage closer to a massive structural failure. If enough remaining cargo bulkheads failed, the wreck could shift from chronic leakage into a major release scenario. Seawater would enter the compromised spaces, and buoyant petroleum product could escape into the water column in volumes far beyond the small intermittent sheens already observed. NOAA's risk modeling treated Coimbra as a site capable of producing serious oiling impacts under a worst-case discharge, even though the exact amount still trapped inside the wreck remained uncertain until direct assessment. The intermittent surface leaks confirmed that the grace period granted by the cold ocean depths was coming to an end. Environmental protection agencies and maritime authorities could no longer rely on the deep water to act as a secure, natural vault for the toxic cargo. Launching a physical intervention to safely extract the oil presented a monumental engineering problem. The heavy oil remained trapped inside a complex maze of twisted steel, and any intervention had to be planned without assuming the weakened hull would tolerate stress. Before extraction equipment could be lowered, salvage engineers first had to resolve the wreck's working geometry. They needed a way to see through the dark water, map the shattered steel, and choose access points without placing unnecessary force on the wreck. Scanning a shattered, heavily degraded debris field required the salvage team to combine old survey data with new inspection tools. Long before the removal phase, a NOAA Multibeam survey had turned the known fracture pattern into mapped survey data. In 2019, the United States Coast Guard, Resolve Marine Group, and supporting contractors used that knowledge as part of a full-scale environmental response. Sonar, remote-operated vehicles, and commercial divers worked together to turn a dangerous historical wreck into an engineering site. Acoustic mapping gave engineers a non-contact framework for the larger debris field. The resulting digital model revealed a chaotic and violently deformed site. The sonar data fixed the orientation of each separated section. The bow section had shifted toward a near-capsized position. The midsection lay heavily over on its starboard side. The stern section also rested on its starboard side, surrounded by a complex scatter of torn plating, twisted pipes, and shattered framing. This three-part fracture pattern documented the massive kinetic trauma of the original sinking, while also showing that the wreck had continued to change under corrosion, bottom currents, and fishing gear impacts. With the macro geometry of the three sections firmly established by the sonar point cloud, the salvage team transitioned to the next phase of the digital resurrection. They deployed advanced remote-operated vehicles to conduct close proximity visual inspections. These robotic systems descended into the cold water, tethered to the surface by long umbilical cables that had to be carefully managed against the constant deep water currents. The surface pilots navigated the remote-operated vehicles through the treacherous and jagged layout of the three sections. High-definition cameras and lighting arrays kept the hull in view, while pilots moved with extreme operational caution. They carefully hovered just inches away from the degrading hull to avoid snagging a tether or bumping a weakened bulkhead. Their primary objective was to safely navigate the outer ruin and visually identify which specific internal compartments had survived. The remote-operated vehicles systematically surveyed the exposed structural framing and the collapsed deck sections. They carefully peered beneath the tangled exterior debris to locate the main cargo and bunker tank areas. Through meticulous visual documentation, cleaning, and later diver access, the engineering team converted inspection into a workable tank list. Of the ship's 32 cargo and bunker tanks, 15 were accessible and appeared intact enough to tap. 10 of those were found to contain substantial petroleum product. The detailed video feeds and diver observations allowed the surface team to map the location, angle, and orientation of the recoverable oil pockets. The combination of multi-beam acoustic mapping and high-definition robotic video successfully converted a dangerous, unknown deep water hazard into a precise engineering grid. The salvage commanders now possessed a working digital blueprint of the 3 sections and the recoverable oil pockets identified by inspection. However, this digital clarity introduced a terrifying new physical problem. The acoustic sensors and robotic cameras could map external dimensions and guide access planning, but they could not prove how much residual strength remained inside the aging 1937 steel. The most startling evidence contradiction facing the salvage engineers was a deep water metallurgical paradox. The aggressive ocean environment was rapidly dissolving the exterior of the wrecked hull, yet the toxic payload itself was actively saving the interior structure. After decades in the Atlantic, the exterior steel had the expected corrosion profile, weakened, pitted, and losing material to seawater. A completely different chemical reality existed inside the targeted cargo holds. The heavy lubricating oil contained within these specific spaces was remarkably viscous and sticky. Over time, this thick cargo evenly coated the inner walls of the steel compartments. The oil smothered every internal seam, overlapping joint, and rivet head. It formed a dense, hydrophobic barrier that physically prevented the cold seawater from ever coming into direct contact with the interior metal. The result was an asymmetric corrosion pattern rather than uniform collapse. In the oil-coated target zones, that uneven preservation created a plausible path to physical intervention, but reaching those spaces still required human work at the seabed. Remote-operated vehicles had successfully mapped and supported work around the exterior debris, but the physical tasks of cleaning, sampling, drilling, capping, and rigging required the tools and judgment of commercial hard-hat divers. The structural targets rested deep on the seabed at a depth of roughly 180 feet. At 180 feet, the ocean is cold, dark, and pressurized far beyond surface conditions. Working under these conditions imposes severe physiological boundaries on a diver. The Coimbra team used surface-supplied mixed gas, including helium and oxygen, to support work at depth. Even with that system, the working window on the bottom was limited. The divers operated in disciplined shifts, often with only 60 to 80 minutes of bottom time, before decompression demands controlled the rest of the dive. Once the planned bottom time expired, the diver could not simply ride back to the surface and walk away. Ascending too quickly through the water column could allow absorbed gases to form dangerous bubbles inside the body. Instead, each diver followed a controlled decompression sequence. That meant staged decompression in the water, followed by time inside a pressurized hyperbaric chamber on the deck of the salvage vessel. The dive was not over when the diver left the wreck. It continued through the slow, disciplined process of returning the body safely to surface pressure. That decompression profile turned every bottom shift into a tightly rationed work period. Inside that narrow window, the divers had to turn survey confidence into a physical breach. Heavy tools, pressurized steel, jagged wreckage, and no room for error. The final physical obstacle was turning that necessary breach into a sealed, controlled operation. If a tool slipped, a seal failed, or weakened plating tore beyond the planned opening, buoyant oil could escape through the damaged seam. To solve this mechanical trap, the engineering team used a controlled extraction method known as hot tapping. The divers did not simply cut open the hull. They cleaned selected access points, installed sealed fittings and valves, and drilled through the contained assembly so the tank could be sampled, capped, and later pumped without opening an uncontrolled path to the sea. Working within their limited bottom times, the divers systematically executed this precision hot tapping sequence across the accessible tanks judged intact enough to investigate. Each successful installation created a secure, controlled portal into a hidden oil pocket. However, breaching the hull was only the first half of the physical problem. The engineers now had to physically extract the heavy lubricating oil from a depth of 180 feet. Getting the oil to flow upward required overcoming the severe fluid dynamics of cold viscosity pumping. The deep water environment had chilled the historic cargo, and some of the petroleum product behaved less like a free-flowing liquid than a thick industrial residue. The salvage crew connected reinforced hoses to the underwater fittings and moved the product to the surface vessel in controlled stages. The lighter lubricating oil could be pumped more directly, but the heavier fuel oil discovered on board required a heating and recirculation system to reduce viscosity and allow skimming and recovery. The engineers could not treat every tank the same way. Each compartment had to be sampled, tested, and pumped according to the type and condition of the product inside. The recovery phase was measured in tanks, hoses, and days. Some compartments took several days to empty. As the dark sludge finally flowed onto the surface vessel, it was safely transferred into modern holding tanks. Over the course of several months, the marine engineers and government authorities steadily drained the surviving sections of the shattered tanker. The grueling underwater labor and careful fluid management ultimately paid off. By the time the final valve was closed and the hoses were detached, the salvage operation had successfully recovered 476,000 gallons of heavy oil from the deep water environment. The targeted compartments were rendered substantially safer, leaving behind only small amounts of unrecoverable residue inside the decaying steel. The immediate environmental threat off the coast of New York was sharply reduced. Yet, as the surface fleet prepared to depart, the recovery pointed beyond Coimbra to a global seafloor crowded with aging wrecks and suspected fuel. With the physical extraction phase complete, as much as 99% of the recoverable oil had been removed from the SS Coimbra. The vessel remained on the seabed, but it had moved back toward the category of a monitored historical wreck. Historically, maritime authorities and environmental agencies operated on a purely reactive basis regarding sunken wrecks. They waited for a catastrophic structural collapse, relying on surface booms, chemical dispersants, and massive beach cleanups only after the deep water containment had completely failed and the oil washed ashore. The sheer difficulty of reaching these deep wrecks, combined with the extreme danger of accidentally triggering a release during an intervention, made preemptive action seem entirely impossible. For decades, the prevailing logic dictated that these sunken ships were best left completely alone. Intervening meant accepting a massive institutional risk. However, the exact engineering blueprint executed during this particular salvage operation fundamentally shattered that institutional assumption. It changed the practical baseline for environmental remediation. By successfully executing a controlled deep water extraction on a heavily degraded structure, the salvage engineers proved that preemptive neutralization is highly mechanically viable. Authorities no longer have to wait for the ocean to finally destroy the remaining steel bulkheads. They can actively hunt down high-risk targets, assess their specific decay rates, and securely drain the lethal cargo before a single drop reaches the fragile coastal ecosystem. This vital shift from reactive surface cleanup to proactive deep water extraction changes the fundamental math of global marine protection. It removes the necessity of fighting an uncontrollable spill on the surface by entirely eliminating the source at the bottom of the ocean. The successful methodology shows that engineers can sometimes interact with ruined vessels, but only after careful site-specific assessment. Thousands of merchant vessels, tankers, and warships sank during the intense global conflict of the 20th century. A significant subset of those wrecks went down with petroleum cargo, bunker fuel, or other hazardous material still aboard. Like the SS Coimbra, many have spent the last 7 or 8 decades in cold water. Some have already leaked most of their oil, while others may still contain dangerous pockets of fuel. The clock is running differently on each wreck, but across the globe, the risk is not theoretical. The successful extraction off the eastern seaboard serves as a stark proof of concept for the monumental task ahead. The remaining barriers are no longer purely mechanical. Information, funding, weather, legal authority, technical planning, and institutional will all decide whether intervention happens before the structural grace period expires. The meticulous engineering matrix used to disarm this specific wreck can inform other high-risk targets scattered across the world, but it cannot be copied blindly from one wreck to the next. Every site has its own depth, corrosion pattern, cargo type, orientation, biological setting, and human risk. The legacy of this mission is the benchmark it leaves behind. The deep ocean is no longer an entirely inaccessible vault. The technology and procedural discipline now exist to assess submerged environmental threats and disarm those that meet the engineering, legal, and human risk threshold. The Coimbra methodology set a demanding benchmark for future deep water wreck interventions,